Good afternoon, everybody, and welcome to the first webinar on CCUS organized by ECCSEL in the frame of the Accelerate project. OGS is leading this webinar and together with Sota Carbo and Syntev speakers. Just a brief introduction with some recommendations during the webinar. Please, all participants, switch off your microphone and camera during the webinar. And of course, questions are welcome, but at the very end of the presentation session. So please, if you have any question, type them in the questions panel and the speakers will answer you after the 3 presentations. Just a brief introduction on what ECCSEL is. ECCSEL is the European Carbon Dioxide Carbon and Storage Laboratory Infrastructure. It is a European research infrastructure. It is an ERIC that is formed by 5 member countries. Norway, which hosts the headquarters, the operation center, Italy, France, UK, the Netherlands. ECCSEL groups 79 world-class research facilities owned by 21 facility owners, and its aim is to close the CCUS knowledge gaps, to contribute to the reduction of CO2 emissions in accordance to the Paris Agreement. So just summarizing, the aim of ECCSEL is to contribute to reduce global warming. In the frame of ECCSEL, the Accelerate project has been funded. It is an Horizon 2020 project with a budget of 3.5 million euros, which will last for 3 years, starting from 2020. This project is focused on the long-term sustainability of the ERIC, and it's aimed to increase the international collaborations, the link with industries, and to empower the national nodes. One of the important activities that will be held during the Accelerate project are related to capacity building. The capacity building work package led by OGS with the contribution of Sota Carbo will organize a very interesting program which will be based on a webinar series that you are here today to follow. Then we will have some specific workshops connected with some popular summer schools, and then some tailored training courses. Workshop and tailored training courses addressed to industry and researchers will start in 2021, but now we will start with the webinar series. Just an overview, we will organize about 16 webinars starting from October 2020. On 4 different topics, so capture, transport, utilization, and storage, spread over the 3 years of the project. And so we are now starting with the first one, related on CO2 capture technologies fit to purpose. If you want to learn more about this capacity building program, please visit our website, www.excel.org for more information. This is today's agenda. We have 3 keynote speakers from Syntev industry, and thank you very much for your participation. Thijs Peters, Blom, and Karl Anders Hoff. Sorry for my pronunciation. I hope I have done it correctly. Michela Vellico, I am Michela Vellico, together with Alberto Pettinau, will chair this session. So I will give the floor to the first presenter, so Thijs Peters, and I'm briefly introducing you. So Thijs Peters is a senior research scientist working at Syntev since 2005. He has completed his PhD in chemical engineering at the University of Eindhoven in the Netherlands, and has started in Syntev shortly thereafter. He has now more close to 20 years of experience in the field of gas separation and carbon capture through membrane technology. He has contributed to many European projects in membrane development and performance evaluation. He has published more than 60 scientific papers, written 12 book chapters, and has contributed to over 150 conferences on this subject. So a very impressive CV. Thijs, the floor is yours. Please go ahead.
So, yeah, first now I am unmuted, so now you will probably hear me. Maybe Michela can acknowledge that, but then we can just start. Yes, my name is Thijs Peters. I'm a senior scientist at Syntev Industry. I will today talk for around 15 minutes about CO2 capture technology by membranes. But first I will talk a little bit first about Syntev, what we are and what we do, before Blom and Karl Anders respectively will take over for the Sorbents and the Solvents. So what is Syntev? Syntev is Scandinavia's largest independent research organization. We are around 2,000 employees, located both in Trondheim and in Oslo. I am myself located in Oslo. Those 2,000 people, they come from 72 nationalities, so we are quite an international organization. And we have worked, at least in 2019, for 3,500 different customers. Our vision is technology for a better society, and we work in a lot of different areas like oil and gas, health and welfare, ocean space technology, but also renewable energy. Close to 95% of our income comes from contracts won in an open competition, which means that only around 5 or 6% of our funding comes from the Norwegian government through the basic funding. All the rest is won in competition. For example, directly from industry, or from project grants from the Research Council of Norway, or from the EU project, because we are a major participant in EU research programs. This shows that we have around 166 projects at the moment, with close to a project cost of 1.6 billion. We are coordinating 43 projects with quite a, let's say, a high value for, at least in the Horizon 2020. But first of all, we are an independent, not-for-profit research institute. So we do not make any more money, and any profit we make is invested again into infrastructure or knowledge. For example, the last 5 years, we have invested a lot in different laboratories, amongst others, infrastructure relevant for CCS, which we have made available within the ECCSEL, which we will talk about now. So in terms of membranes in energy systems with CO2 capture, it's in that we work on a lot of different membrane technologies relevant for, let's say, post-combustion, pre-combustion, and membranes relevant for oxyfuel. Either polymeric membrane systems or, let's say, more high temperature ceramic or metallic membranes. Most of them are either selected for oxygen, hydrogen, or CO2. That's maybe the main gases we work on, in addition to membranes relevant for natural gas sweetening, which is the one to the bottom there, CO2 methane separation. So in a post-pre-combustion context, they can either be applied on the exhaust gas coming out of a cement plant or turbine, a gas turbine, or in relation to in combination with the water gas shift in a pre-combustion manner, or to, let's say, generate oxygen for oxyfuel processes. So if we start with the post-combustion membrane systems, then we work a lot on different processes. We work on the membrane development in itself. We work on how to evaluate their performance under real conditions, and we work on, let's say, we investigate how to integrate them in a techno-economic way in a real process. And then you have to take into account the membrane properties, the performance, but also the cost to come to a proper process design. We have a quite substantial polymer membrane research facility. This shows some equipment that is available within Syntev Industry in Trondheim to do flue gas membrane testing, we have equipment for compact hollow fiber spinning. We have a high pressure gas membrane test rig relevant for natural gas sweetening, and a more large scale pilot scale membrane test rig. All of these are made available within the ECCSEL framework. If we want to test the membranes under more real gases, including gaseous contaminants typically present in a flue gas, for example, or in natural gas, then we have also a special gas laboratory where we can test the membranes in the presence of, for example, H2S, SO2, or ammonia. Because of those gases, there is a large focus on obviously on the HSE. This slide gives some examples of investigations we have done in some of the projects we have been involved in. For example, a membrane process relevant for flue gas treatment. Often you have certain levels of SO2 there, so we have tested the membrane under long term in the presence of SO2 up to levels of 400 ppm in the special gas laboratory, which I showed in the previous slide. Also, in terms of membranes for natural gas sweetening, we have tested membranes we have made ourselves, or either commercial membranes in the presence of high H2S levels. The graphs there shows the membrane performance during the introduction of, for example, 5% of H2S. So this shows a little bit the possibilities we have in relation to the post-combustion membranes. So if we continue with the pre-combustion membrane systems, then at SINTEF we have worked a lot on ceramic membranes. Ceramic membranes either relevant for air separation, so oxygen selective, or membranes selective to hydrogen, proton-conducting membranes. We have worked a lot there together with the company, making those membranes and making them and testing them in different processes, for example, hydrogen production from natural gas with CCS, but also in a process where they make aromatics and hydrogen from natural gas. In those projects, we have established pilot production lines, but also substantial test facilities. In terms of ceramic oxygen conducting membranes, they are tested a lot, and they have reached a high TRL scale in terms of oxygen production. But for pure oxygen production, these membranes are maybe not the most optimal. Maybe they're more optimal for syngas production. In terms of the hydrogen selective membranes, then we have worked a lot with a company called Costech Membrane Sciences that have then developed a process for electrochemical hydrogen separation and compression based on electrochemical membrane reactors, where the operation of the steam methane reforming is balanced with the heat involved from the operation of the cell itself. So this is a membrane integrated SMR reaction where you simultaneously can get a high conversion and yield of CO2 and can produce the hydrogen at a high purity and high pressure. As I mentioned, we have also for the ceramic membranes unique infrastructure in terms of the manufacturing of those membranes. They are typically made by extrusion followed by coating, and all of these are done within the clean room facilities that we have here. Also, these membranes can be tested in the presence of more dangerous gases in the special gas laboratory that I mentioned. In terms of metallic membranes, we have worked a lot on palladium-based membranes that are relevant for high temperature hydrogen separation, typically operating temperature between 300 and 550 degrees C. The scientific challenges and the activities we have had are mostly related to lifetime issues, the stability of those membranes against contaminants, and also the long-term operation. What is really happening if you operate these membranes over a period of 1 or 2 years? What is happening with the microstructure? We have worked on the module design and also on the upscaling of the membrane technology in itself. For these, we have also good test facilities, and lately these membranes have been tested at the methanol synthesis plant here in Norway. So conclusions, very, very rapid, is that we have good facilities and large activities on membrane processes in gas separation, production and use. We have all the equipment available to test membranes at realistic operating conditions, and questions or inquiries at a later stage you can direct to me. So here are a lot of acknowledgements of different projects and financing institutes, and then it's the next presentation. Thank you.
Thank you very much. Thank you very much, Thijs. Thank you very much. Very interesting presentation. Let me introduce you, Richard Blom, senior researcher, scientist in the Department for Process Technology at Sintef Industry. He completed his PhD in physical chemistry at the University of Oslo. He then became research scientist at Center for Industrial Research in Oslo, where he worked on several projects about catalysts and porous materials. For the last 15 years, he has been working on topics related to energy storage, gas separation in porous materials, development of novel processes for separation utilizing solid solvents. Richard Blom holds more than 15 patents and patent applications, more than 115 publications, more than 20 oral contributions on international conferences. Richard, the floor is yours.
Thank you, Michela. Let me see. Have I received the sharing possibilities? Thanks. Okay, do you see it now?
Yes.
Yes.
Yes, thank you. Thank you. So I'll talk a little bit about solid solvents used for CO2 capture in a similar manner as Thijs. First, I will tell you a little bit about the different solvents we are talking about, the different kind of materials used for CO2 capture. Then I'll go into a little bit about the process, different processes. It's a number of different processes that can be used to regenerate that solvent, which is the most critical part. And then I'll give some info about what I see as a workflow in the development of solvent-based technologies. This is a place where you will need infrastructure in the way to get through. And at the end, I'll give some final remarks. So this is, in my view, the kind of actually the major families of solvents for CO2 capture. On the right side here, you will have the high temperature solvents, typically calcium oxide-based adsorbents, which cycle between calcium oxide and calcium carbonate, which need a high temperature to regenerate. And also lithium zirconate is one of these high temperature adsorbents that will need a high temperature for regeneration. You have also intermediate temperature adsorbents like hydrotalcides. This is the one used for example, solvent-enhanced water-gas shift reactions, where you capture the CO2 typically at 400 degrees. This is a layered mineral, so it's not changing the properties so much during cycling, in contrast to the calcium oxide, for instance, where you really change the material significantly from oxide to carbonate and back and forth like that. So it will give a lot of internal stress in the material. On the left side here, we have the low temperature adsorbents, which are split into 4 different classes or families. We have the already commercial, I would say, zeolites, microporous materials, fully inorganic, and also activated carbons, which you can buy in tons at the moment, and this might have an application somewhere. But the new ones, let's say that you have somebody that I would call the supportive amines, as shown up here. There's many ways to support amines on a support, but you need a high surface area support, and then you have to either graft on the surface or impregnate onto the surface the amine moieties, different kind. For example, polyethylene imine is much used for that. And then you have the huge class which are called the MOFs. This can also include other kind of organic framework materials like porous polymers and so on. But it's a lot. It's a huge family because it actually contains a whole periodic system of elements together with the whole organic chemistry, and then you can just think about all the kind of porous materials you can make from that. Common for these is that they can absorb. It's more physisorption we talk about. So they typically absorb at ambient temperatures, 50 degrees maybe, and 70 degrees maybe for the pay kind of adsorbents. And then you have to either regenerate it, but everything happens, within 150 plus minus ambient to 150 degrees in these cases. So yeah, there are many possibilities. So if you go to the process, as I said, you really need to, you can't have a once-through process, I would call it, where you capture the CO2 and just let it be there and grow it down on the ground or something like that. You really need to recycle your adsorbents in a fast and cyclic manner. So one way to do this is to increase the temperature of your adsorbent. First, to adsorb at low temperature, shown by this isotherm here, maybe at this, let's say at 15% CO2, you will capture it with this capacity. And then you need to heat the adsorbent, let's say to 400 Kelvin as shown here, and then actually you want to release a quite pure CO2 stream, so it'll go in this direction. So actually the difference between this point on the y-axis and this point on the y-axis will be the kind of maximum working capacity of these adsorbents as is shown here. And then you cool it down and reabsorb and so on. So this will take a certain time to do this cycle. Another way to do this is to reduce the pressure. In this case, if you look at the blue isotherm here, you can adsorb at high pressure, and then you can desorb at the lower pressure as shown here. And then actually you have this potential working capacity as shown between these two lines here. So these are two ways, and also you can actually mix the two. You can use both a little bit temperature and some vacuum to regenerate the adsorbent. And this is one of the critical steps. You really need to find the best way to regenerate the adsorbent, because that's where you have to put in energy. Adsorption is spontaneous, you don't have to work for that, but releasing it again is where you have to put in the work. So when you should choose an adsorbent, this is not a simple task, because if you look at a variety of adsorbents, as shown some isotherms here, but you can get all kind of isotherms. You have this S-shaped isotherm as the blue one. This is a high pore volume MOF. This green one is a zeolite, and the red one is a carbon, activated carbon. And if you see here, I'll see the blue one looks very nice for high pressure use. You don't adsorb very much at low pressure, so this is no good. But if you go to high pressure, let's say 20 bar of CO2, you can certainly adsorb a lot. And then you can release it at least 5 bars, and you will still have a very good cycling capacity or working capacity in that case. If you want to adsorb at very low pressure, you probably go to something that looks more like the zeolite isotherm, with it's quite steep in the beginning, and then you can actually capture CO2 at this point, for instance. Activated carbon also is working mostly best at high pressures there, because it has this quite linear shape where you can adsorb at high pressure and get a certain capacity when you go down in pressure. So actually the shape of the isotherm is the first thing you look at, when you want to choose a adsorbent for a process. But certainly you need to know what kind of gas you have to capture the CO2 from as well, which is very important. The boundary conditions for your process. So all this goes hand in hand in a way. It's very close connection between the adsorbent and the optimal process to use. So activity certainly is you need to have something that with the surface that really binds CO2 stronger than nitrogen first, and also other components present. And water it would be very nice to have something that is more selective for CO2 than water, but this is very, very, very rare. The polyethylene imine adsorbent has that to a certain extent, but still it will adsorb water. But in that case, the adsorption of water doesn't affect the CO2 adsorption that much. So it's still good to use that at a certain pressure of water. And also physical stability of the adsorbent is very important, because if you use it in a kind of fluid bed system, for instance, attrition will be important. Also chemical stability if you have a real flue gas with SOx, NOx, water vapor, and whatever you like, I mean, you really need it to be stable for a lot of time. So this slide show in one page, in a way, what I mean with the development workflow in the development of solvent-based technologies. You know, what you do is you start with the synthesis of a powder. In most cases, you have solids made in powder form in autoclave or glassware or whatever, but you end up with something which is quite fluffy, and you can certainly not use that in a process. What you do, you need to first be certain that you really have the right powder. So you need to do XRD, you need to measure the surface area and all these things to be certain that it's and you probably also would check it, you know, how much CO2 does it absorb and so on. Maybe water absorption also on this powder. But quite early you need to think about shaping, because in the real process you need to have shaped bodies, because you don't want it to follow the gas flow out of the reactor. You want it to stay there and do the job. So you need to do some shaping. You need to find out, you know, for this process, what kind of shape should it have. So you do the shaping, and then you have to measure it again, you know, the isosems and all this to check that, okay, the shaping, the material is okay, even if you shaped it, you know, because it could involve some temperature, some pressure, and all this. When you do extrusion, for instance, it's very easy to destroy a soft material. So you need to do all kind of measurements, and this kind of measurement, when you think about equilibrium measurements, all the isotherms you will need, and also the kinetic measurements, how fast do the gas flow through your pellet. This is what you need in a way for process modeling. And when you have that, you can actually model the process and try to find the optimal process for this adsorbent, for a certain gas flow, flue gas, incoming flue gas. But at some point you will also need to know the stability of the adsorbents, which I show here. This is only 20 cycles, but still you really need to go into the stability, multi-cycle stability, and run it for as long as you dare, you know. So this looks very nice in this case, but you really need to go further than 20 cycles. I mean, 1,000 cycles is good at very realistic conditions to be certain that, okay, this can actually withstand maybe at least a year in the reactor. And when you did all this modeling, stability checks and all this, you set up, in this case, I've shown here a typical scheme for a vacuum swing adsorption process, where actually you have several columns. You might have, in this case, have 6 columns, and one of the columns is always in the red, which is the adsorption mode. So this is a continuous process. But the rest of the time, you have a short time with adsorption mode, and the rest of the time is actually regeneration of your adsorbent before it goes back to the first step here. So what you can do when you made your model, you can actually go to a small process, checking out your model, verifying your model results by doing testing in a real small-scale lab reactor. So this is what I see the workflow, and here, I mean, all kind of up here you see all kind of characterization equipment. You have an oven that you probably use, and a small extruder to check out the ECCSEL making extrudates. You have a spray dryer for making particles, and so on. And certainly over here you have more equilibrium measurement equipment. You have reactors, start to have reactors. You have here a 8-bank, we call it, where you can measure 8 different reactors, breakthrough measurements and cyclic experiments at 8 materials at the same time. And then we go further on here to a chemical looping combustion reactor here. Here we have a 4-bed PSA reactor, which is inside this oven here, and so on. So what we do here is actually to have, we need all this equipment in a way to do the job, to come over here and check out, you know, the final step when we really find a good process. So I'll say a little bit about shaping, because this is something that people seem to forget. I mean, there's so many papers out there where everything is done on a fluffy powder you made straight from your lab, and you don't actually know anything about how it can be used in real life. So shaping is extremely important, and there are many ways to do it. Even for soft materials, there are quite good methods out there. And we have been working on quite a number of these, as shown here. And also, I think quite recently we started working on 3D printing of adsorbents, which is also a kind of promising thing. If you really want to go to high gas velocities and low cycle times in the process. They have this a 4-column PVSA reactor that can be used for testing out modeling results, the validation of the modeling results, which is working quite nice. This is kind of small scale. We need something like, I think it's 60-70 gram shaped adsorbents in each column. It's about 1 inch in diameter. So, and it can go to very high pressures like 70 atmospheres. And this is typically the pressure that it can be used for natural gas sweetening also. So it's not only CCS in a way, but also sweetening experiments. So it's very versatile, I'd say. The newcomer in the lab, in the testing lab, is a moving bed TSA process that we're just about to finalizing now. We're testing it out, which is a kind of quite unproven technology, I would say. Very few of these reactors in the world. Where we have first we have an absorption section up here, a feeder. You feed that solvent through a screw here at the constant rate. You absorb the CO2 here, move it into the desorption section. This one, very heated up to a certain temperature to release the CO2. It goes out here, and then you have to cool it down again down here before you transport it back up to the silo up here for a new cycle. So this is something we have been working on for some time, and I think we have found a good, quite good setup, which uses something like 10-liter shaped adsorbent. In this case, is a much smaller sphere you can use. I mean, typically around 1.5 millimeter spherical shaped adsorbent in this case. So I think that was, well, here it is in real life, where you see the black one up here is actually the adsorber, and the heating part is here, well packed, isolated, and the cooling pack part is down here. Then we have actually a pneumatic transport back to the top. So I've given you a taste of what we have and what is important when you develop solid solvent-based technologies. And I think each adsorbent needs to be treated in its own way, in a way, in this world. So I think if you are working on this and need some expertise and you need to have done some experiments in this, please take contact, and then we have to discuss what you need, and then we can probably help you on some of this, and you might also do some in your own lab. So I think here are my contact details, and I wanted to, yeah, thank you for your attention. That's it.
Thank you very much, Richard. Really interesting presentation, very high level technology, and so thank you. I would like to remind all the presenters, all the attendees, that they can type their questions in the question panel during all the webinar. Only the answers will be given at the very end of the webinar. So please, if you have any question, type it in the questions panel. Okay, let me introduce you, Karl Anders Hoff, senior researcher scientist at the Department of the Chemical and Environmental Process Engineering at SINTEF. He completed his PhD in chemical engineering at NTNU. He has 21 years of experience with gas separation, specializing on membranes, absorption processes, and solvents for CO2 capture. His experience spans both the experimental characterization and the modeling of novel solvents and absorption processes. He has been project manager of major national and international projects on development of reactive absorption systems for industrial application in CCS. Karl Anders, the floor is yours. Please go ahead. We can't hear you, Karl Anders.
Sorry, I was muted. So I'm starting again. So I will go through some important experiences from working for many years on development of reactive absorption systems for CO2 capture. And I will highlight elements of the workflow in development of these systems, but also the importance of infrastructure in this development. So reactive absorption is the capture technology which is being used in the very first full-scale capture projects for CO2 internationally. At Boundary Dam, at Petronova outside of Houston in the US, and also at Northern Brevik in Norway as part of the Longship, the Norwegian Longship project. And in Northern Brevik, they will use solvent-based technology developed by Aker in cooperation with SINTEF, developing the solvent, which is the working media in this process that we see to the right here, where the reactive solvent cycles through the process and captures the CO2 in the absorber. A basic feature of this technology is that the energy is supplied as low-grade heat in the reboiler, and it enables utilization of excess heat, which is very important, a very important feature of reactive absorption with temperature swing. Another important feature is that this process not just separates the CO2, captures the CO2, but it also compresses the CO2 thermally. Without using mechanical work, the CO2 leaves this process at a pressure of at least 1.5 bar, even up to 10 bar, depending on solvent and process operating conditions. And this is also a very important feature, since the liquid CO2 will ultimately be the end product for most of these capture processes. It's also highly scalable in terms of numbers of tons per year that is captured. But in any case, the key to the performance is the solvent chemistry and the solvent formulation. But talking about energy requirement, I also want to emphasize that there has been a significant development in this technology towards lower energy requirement over the last 15 years. And we're closing in on the line for a theoretical minimum energy requirement, which we will never reach because that's what we call a reversible process, but we can get as close as possible to this line, and we're closing in terms of the thermodynamic efficiency of reactive absorption systems. For the solvent, basic feature you need is, of course, a certain absorption capacity with the flue gas that you're dealing with, whether it's from coal or from natural gas or from other process industries with dilute CO2 in the flue gas. You need a certain capacity, and here we see two solvents, one with a very high capacity both for a typical coal-derived flue gas or a natural gas or dilute flue gas, and another solvent with low capacity. So you need to choose a solvent with the capacity. You also need the solvent to have a certain temperature dependency of its absorption capacity in order to drive a temperature swing based absorption process. So these are basic features, but there's lots more to it than absorption capacity. And I will not go through all these boxes in detail, but you need certain kinetics, you need a certain, you need to relate to the molecular weight per ammonia amine functionality, and basically you need to optimize all of these properties in a functional solvent. And in addition to these 7 criteria, which is based upon things that you can measure in the lab, you can model, and you can deduce these properties and optimize them. You also need to relate to other properties which are essential in operation. In terms of, and then I'm talking about degradation, performance, degradation products, corrosivity, cost and availability, and HSE. So these are all altogether 14 criteria that a functional solvent needs to fulfill. A workflow for development of solvent systems for this process should start by evaluating a large number of solvent candidates to build a solvent formulation, and then performing a screening test to investigate the fundamental performance in terms of absorption capacity and temperature dependency. Then, from our experience, it's very important to do degradation testing at an early stage, and preferably before you go to the detailed measurement of VLE, kinetics, and viscosity, which are more labor-intensive and costly measurements. And then after that, you go further to developing a process simulation performance tests and preparing for pilot testing and where you learn more about the performance. And on the way, you do more VLE, more kinetics, viscosity as needed, and finally you will be able to do a detailed modeling and prepare for a test at larger scale. So in this to the slide to the right, we see the illustration of working from the molecular level via degradation testing, basic VLE measurements, and finally the lab the pilot testing. And here we see a picture of our Tiller lab facility or pilot facility here in Trondheim, which can study these solvents in a full height operation, capturing 90% of the CO2. Back to the screening stage, what we are looking for in the functional solvent is a combination of a high cycle capacity and a high absorption rate. So we want to be in the upper right in this picture. In addition to that, when talking about solvent degradation, we have a number of instruments to study process relevant degradation performance in the solvent degradation rig, which is to the upper left, and also dedicated apparatuses for oxidative and thermal degradation. This performance is also quite essential to investigate. So we are looking for obviously low tendency to degrade oxidatively and thermally, looking for systems in the lower left in this diagram. As I said, this test should be done at an early stage in solvent development. Finally, I'm back to the pilot testing, where you get the full performance and a lot of information in terms of energy requirement, emissions performance, degradation performance, and you also get a lot of results that you can use in a simulation model to further optimize the process performance. And to that, we use our own simulator, CO2 Sim, which is a rigorous advanced process simulator developed by SINTEF, where we can do process performance evaluation and optimizations with new solvents. This tool holds rigorous thermodynamics and the mass transfer models, and it's a rate-based model for all systems. For example, one thing that we can see from working with CO2 Sim is also from the thermodynamic model, we see how the full energy requirement, the combined energy requirement as the specific reboiler duty is actually a compound of 3 different terms: the heat of desorption, sensible heat, and the stripping steam energy requirement. And we can see here that the desorption energy, the green, is the biggest contribution to the energy requirements, and this is obviously due to the heat of reaction, which is the dominating term in the reaction in the desorption energy requirement. So that was a quite fast walkthrough of the main elements of solvent development. So I just wanted to to summarize this briefly, so the number of criteria that must be addressed to qualify a single solvent for industrial application, it's very large. There are many solvents that can show potential energy benefit, but you need to evaluate degradation performance. You need also to document low risk of emissions, and you need to close the nitrogen balance from degradation testing and working on the degradation chemistry. It's also important to note that the energy requirement that is an important feature of this technology. It's not a solvent property as such, but it's based on the process configuration and the process performance and operating conditions. So that has to be optimized and analyzed deeply. Still, the recent work on solvent development has really enabled a significant increase in the thermodynamic efficiency of post-combustion capture. And as I said, the technology is put into action in industrial full-scale projects as we speak. So that was my final conclusion. Thank you for listening.
Thank you very much, Karl Anders. Okay, now it's time for question and answers. So I kindly ask all the staff, so all the presenters, and to Alberto to stay online and to answer to the questions our attendees are going to ask us. Okay.
So good morning, everyone. There's a first question for Richard. Could you please explain what you mean by shaping? The author of the question says, am I right assuming that you refer to the size of solid particles, or does it relate to something else?
No, I think that's correct, but it doesn't only have to be particles. I think it's important that, I mean, when you make material, in most cases, it's a kind of fluffy powder, which will follow a quite low gas stream out of the reactor if you put it there, and you don't want that. You want it to stay in the reactor, so it needs to have a certain size in a way to stay there during the capture conditions. But I mean, to find the right shape, I mean, one thing, I mean, if you do extrusion, for instance, you certainly make pellets, which is kind of slightly banana shaped, you know. But also you want to maybe, it might be that you get a better flow pattern through your column if you have a different shape or a more optimized shape. So that's why I mentioned this with the 3D printed adsorbents, because in that case you can actually first model the shape, the optimal shape, where you have the perfect plug flow through the column, and then actually you can use that, the drawing from that model to print it, and in principle you can test it out if your adsorbent is printable somehow. That's certainly also a big topic to work on. So it could be any shape, not only particles, but also, you know, honeycombs type shapes or even more advanced. But the first thing is actually to make, let's say, for a VSA, for instance, 3mm spheres or pellets. Yeah. Was that the answer?
Thank you very much. There are several other questions. In particular, 3 questions, again for Richard. So the first one is, how multi-component absorption isotherms are measured, as getting the accurate bait outlet flow rate will be challenging?
Is that, I mean, I guess the person talk about the breakthrough measurements, where you have a gas flow going into the column, and then you certainly adsorb and change the gas velocity through the column in a way. Is that? So what we do there is actually to measure the gas flow out of the column. That would be the best. So you know what comes out, because you have to kind of adjust for that in your modeling. Is that? I mean, yeah.
Oh, okay. I assume you replied to the question. So the second one is very similar to the previous one. Can you please elaborate the importance of shaping? I don't know if you had something to add.
I mean, shaping is a technology in itself, and I think what I wanted to show is that many, especially the new adsorbents, like metal organic frameworks and porous polymers, these are quite soft materials. So if you try to use the traditional shaping methods like extrusion, where you have quite high temperature and also high pressure, or other methods, I think you can have problems, because you might have a big reduction in your surface area, so you actually partly destroy your material, which you certainly do not want. So you want to find a method where you really keep the nanoporous structure of your virgin powder. But this is not simple, and especially for MOFs and similar materials, we have worked quite a lot of this with this now, and there are ways, but to get really strong particles, that might be a challenge for some materials.
Thank you very much. And the other question, again for Richard, is for PVSA system simulation, which package is generally used, and does the standard cycle sequence like Skarstrom, etc., used to start with?
Yeah, I think I'm not an expert in this, but I mean, we use we have a couple of people using GPROMs, which is I think very good for that kind of modeling, but also a guy working in MATLAB. So I think you can use any to make your code in a way. You can use a lot of different packages, and certainly, I mean, starting with the Skarstrom cycle is probably what you do in most cases, and then you develop that. Yeah.
Okay, so two of the attendees asked if you can provide some consideration on the comparison of these three approaches for CO2 capture, with particular reference to membranes and liquid solvents.
Who should answer that one? Thijs, maybe? No, who is that for? The question. Is it for the panel or is it for the?
It is for all of you.
Okay, good.
There's
yeah.
no specific.
Okay, I can say a few words. Richard can go on. So I think the question, it's a difficult question to answer, because I think both these technologies, they have their merits in particular applications, and one good thing about CCS nowadays is that CCS is relevant for many different industries, for many different types of flue gases, and so to answer that, it depends on energy availability, the CO2 concentration in the flue gas, other impurities, and many things, including the scale of the amount of CO2 to be captured. So that actually takes some works to identify the best technology for a certain industry case.
Thank you very much. There is another question for you, Karl Anders. Is it possible to extend the SynTAP model to membrane contractor as well, or it is limited to traditional absorption columns?
As it is perfectly possible. That's also a very good question, because I actually did my PhD on membrane contactors and modeling membrane contactors. So that model has not been fully integrated with CO2-SIM, but we consider CO2-SIM to be a research platform, and so it's a dynamic software infrastructure that we work on, and can certainly include membrane contactors.
Thank you very much. There is another question for all the panelists. So what is the highest TRL of membrane and sorbent technologies available today for post-combustion capture?
Should I start, Thijs? Yeah, I mean, for sorbents, it's I mean, there are a couple of vacuum swing absorption post-combustion systems, one in Shanghai and one in Australia I know about, which probably that's with real flue gas, so let's say it's TRL6, I would guess. And then we have I mean, the Svante system, which probably is at now TRL5, maybe 6 as well. You know, the rotating bed thing. So it's very dependent on the kind of process and also the material, actually, because you have to, when you go to that size, you really need to make a lot of material, maybe 100 kilos and things, and then you are still stuck with quite the traditional adsorbents. So maximum TRL6, maybe 7. It depends.
Tutto frizzato io.
It's
Tutto frizzato.
Okay.
membrane stays. You're muted.
I think you're still muted.
We don't hear you, Thijs.
Now it's okay.
Okay.
No, still not? Okay, now it's okay. Now, in terms of membranes, it's TRL7, I would say. MTR in the US, they have tested that 20 ton per day membrane system in an operational environment, so that is TRL7. Yeah.
Yeah.
Are there any other questions?
Perfect timing, yeah.
Yeah, definitely.
Sorry, yeah, here we are. Sorry, I had some connection problems. Good. Any other question, or can we conclude the webinar?
I think we can conclude it. Michela, there is a question about the availability of the presentations after the webinar.
Yeah, the webinar will be recorded and the presentation will be available on ECCSEL website. In just wait for a couple of days that we are well, just that we finalize our makeup and to the web, to the presentation, to the webinar, and to the presentation. So okay, if there are no any other question, I would thank all the presenters for being with us today. Thank all the attendees to be with us. Please follow the next webinars, and for more information, visit our website ECCSEL.org or visit OGS website or Sota Carbo website. You will find all the information there. So thank you very much and have a nice day. Bye-bye.
Bye.
Bye-bye.
Thank you very much. Bye-bye.